All right, so for numbers 3, 4, and 5 here, this is off the worksheet that you guys did for review for buffers, KSP, and more. I wanted to review 3, 4, and 5 because these were good buffer questions, and it's been a while since you guys have covered buffers. It was our very first part of our notes for the unit, but let me just walk you guys through it here. So remember, the key component of a buffer is that you're always going to have an acid or a base with the conjugate, and that way a mixture of those two things, and you want to get them usually around at the same molarity as well. But when you have a mixture of something like that, that is considered to be a buffer. Purpose of a buffer, you guys remember, it's to decrease the amount of pH change, and this happens because the acid component and then the base component of the buffer, they're both going to suck up, either not suck up, but they're going to react with the acid or base that's added to the solution. So let's start off with number 3. This one's just a basic pH calculation of a buffer, and you're told that you have 0.20 molarity of the NaH2PO4, and this part right here, the sodium ion, I know I could just ignore, and this is going to make this out to be H2PO4 with the -1 charge because the sodium had a +1 charge. And you also have Na2HPO4. So similar here, when you put these in water, because of the sodium, they're all going to dissolve. And the sodium ions I could just take out and ignore, even though they are just spectators inside the solution that you're looking at. This time here for the HPO4, there were 2 sodiums that were attached, so I know that that has to be a -2 charge. And from this point here, you should be able to assign which one is your acid and which one is your base. H2PO4, negative, even though it is a negative charge, this one is an acid because it actually has one more hydrogen than the other one. The HPO4 -2, it has one less hydrogen than the other one, so I know that this is going to be my conjugate base. You're given your acid dissociation constant right here of 10 to the -8, and the pH of 7.51 is our answer that we're trying to solve for. So basically, anytime you're looking for a pH of a buffer, you could just go straight to the Henderson-Hasselbalch equation. You could set this up by doing a Ka problem, and you could look at the products over the reactants, get hydronium, and then negative log that to get your pH. But this is just a little bit shorter, and I like to use this equation when I can. So pKa plus the log of your base over acid, and you will always be getting the pH equation on the AP exam, so you guys don't need to memorize it. The POH, remember, is pKb, and then you swap this, so acid on top, base on the bottom, and you're just going to go through, we're going to negative log my Ka value right here, the 6.2 times 10 to -8, and then we're going to add that to log of my concentration of base divided by concentration of acid. And the base concentration you had up here, it's 0.40. And the concentration of the acid we had up over here, which is 0.20. So basically it's plus log 2. And if you go ahead and punch this all out on your calculator, and we're going to go to 2 significant figures, we end up getting a pH of 7.51. And those right there are our 2 sig figs. For number 4, this time you're solving for the hydronium concentration, and you're given your 2 things to look at. We have my C2N2H8, and then on the other side, you have your C2N2H9, and look at the ion this time that's going to fall off. When this gets put into water, knowing what you guys know about solubility rules, you know that it will completely dissolve because the chloride here. And for the chloride, it has a negative charge, so when it falls off, you're left with this as a positive charge. Okay, so same idea as before. You want to assign what the acid and what the base is going to be here. The one that is less negative or more positive, we're going to say is going to function as our acid, whereas the C2N2H8 then would have to be our conjugate base. Okay, and we're solving for hydronium. you're given your Kb value. And for this one as well, I'm just going to use the Henderson-Hasselbalch equation just because it's a little easier for setup. But if you didn't want to use it, you could use your set up a Kb equation and then go products over reactants, and then go ahead and solve for hydronium once you know the hydroxide concentration. It's the same step, but I think this one's just nice because you get to do it all in one go. So our POH is pKb. You don't get the POH equation for the AP test, but just know that, you know, the Ka swap for the Kb, and then instead of base over acid, it's acid over the base this time. And we're going to just go through and solve. It's negative log of my Kb value of 4.7 times 10 to the negative 4. And we're going to add it to the log of the concentration of acid over base. So here you could tell that it's really important to be able to determine which one is your acid and base, because if you end up swapping that, then you'll get the wrong ratio put into your equation. And our acid concentration is the 0.35. The base concentration that we have is 0.15. And if you put this all into your calculator, you're going to wind up with 3.695. This is my POH value, remember? So pH we know is just 14 minus the 3.695. I got 10.304. And from here, if you wanted to solve for the hydronium, we're going to do our roadmap 10 to the negative pH. And when you do 10 to the negative 10.304, you're going to wind up with 5.0 times 10 to the negative 11. 2 sig figs, because I'm going with 2 sig figs from the problem here. And then finally, they're telling us about preparing a buffer, and we're given concentration of my base with the volume, and then same thing, concentration of your acid with the volume. And we're solving for pH, and we also know our Ka value over here. Okay, so all I'm going to do is I'm going to take my acid, my acetic acid here, so my CH3COOH, it's getting reacted with my base. You could write NaOH, but I'm just going to concentrate on the part that really reacts, which is the hydroxide. And this is pretty much your equation. You end up getting water. We get our conjugate base. Okay, and I'm going to go ahead and set up a quick bird table because this is not an equilibrium issue that's going on. You're looking at acid and base reacting together. So you could almost think of this as pretty much the same idea as our titration problem. You have a weak acid right here, my acetic acid, and you're reacting it with a strong base. So I need to figure out what the concentration is going to be at the end of the point where you guys react these two together, and then we could go ahead and find out what the pH is going to be here. Okay, so this is bird. The water we could ignore. Okay, and we do need to figure out what these guys are here, the concentration of my acid, the concentration of the base. So I could go ahead and proceed, and I think I told you guys that this is the part where most people kind of tend to make mistakes. So I want to do that really carefully with you guys. The hydroxide concentration from my NaOH, from my sodium hydroxide, it's going to be the molarity times my liters right here. So we have 0.3 liters, and we're timesing it by 2 molarity. We need to divide this by the total volume of the acid and base that's been added. So we have 300 mils and 500 mils. That's going to be 800 mils total volume. But in liters, it's going to come up to 0.8 liters. Okay, so if you multiply and divide by 0.8, we wind up with 0.75 molarity right here. And same deal, we're going to do the same thing for the acid. And we're going to take the volume, which is 0.5 liters, times it by 2 molar, and then we're going to divide it again by the new total volume, which is 0.8. So we have 0.5 times 2 molar, and we're going to divide it by 0.8 liters. And we wind up with 1.25 molarity. Okay, so these two numbers we're going to go ahead and stick into our little bird table. We have 0.75 molarity right here, and we have 1.25 molarity for my acid. And we have 0 of this initially to start off. And knowing what we know, we're going to try to see which of these reactants are going to run out first. And my hydroxide here is going to serve as my limiting reactant because we have the least amount of it. So it completely runs out. It goes to completion. We're going to subtract out 0.75 molarity over here on the left side as well. And when you subtract that out, you wind up with 0.5 molarity. And over on the right side, we're going to add on 0.75. So we get 0.75 molarity here. And at the end of the day, we really just wanted to know this. Okay. I'm trying to solve for the pH here, and we know we could go back and just plug this all into our nice little Henderson-Hasselbalch equation. But in order to do so, I need the concentration of base and I need the concentration of acid. So if you guys take a look at this, I know that 0.5 is my acid. And then my CH3COO is my conjugate base. And now we are ready to just plug in. So the second part of this, and again, remember, anytime I use the Henderson-Hasselbalch, you could just go ahead and go straight for the Ka equation and then solve for hydronium and then negative log that. So if you want to look through our notes, we did the problem initially that way. And either method is completely acceptable. So we have base over acid. I'm going to negative log my Ka, which is 1.8 times 10 to negative 5. And we're going to log the concentration of base over acid. So it's 0.75 divided by 0.5. And we wind up with a concentration of 4.92 as my pH. And we could stop once we have that right there. Okay. I have about 3 minutes left in the video, so let me go ahead and actually just finish off number 6 as well. It's kind of going off of what we looked at here. So this is a titration problem, and number 6 is looking at hydrochloric acid, sodium hydroxide. You know this is strong acid and strong base, but we can't just go straight to the MAVA-MBVB equation because you're not dealing with a neutralization where the amount of acid is equal to the amount of base. They just want to know what the pH is after 28 mils of sodium hydroxide have been added. And you know it's not neutralization because the molarities are the same, but the volume is different for the acid and the base. You have 50 mils of hydrochloric and 28 mils of NaOH. So this isn't going to be just a straight MAV equation. So I'm going to set up a bird table again just to get this going. Okay, so for my bird table, it's just before reaction done. And water we could go ahead and ignore. I'm looking for the concentration of HCl to start off with. It's 0.05 times 0.5 molarity divided by 0.078 liters total volume, and it's 0.32 molarity. Concentration of sodium hydroxide is going to be 0.5 times 0.028 divided by total volume, so it's 0.18 molarity. So we're going to just throw this into our table. We have 0.32 molarity, 0.18 molarity. Initially, we have a 0 of this. I'm going to run out of my base first. And we end up with 0, 0.18, and 0.14 molarity here. Now, the final part of this is we're trying to calculate what the pH is going to be. And just looking at the setup, we do have sodium chloride in the solution, which kind of doesn't matter because chloride is a weak conjugate base of the acid, but I have 0.14 molarity of my hydrochloric, which you know is strong. So basically my hydronium concentration is equal to this number right here. And to get my pH, I'm just going to negative log the 0.14, and we end up with 0.85 here as my final answer. And we're done.